Welcome to lecture 6.7. This is actually a follow-up lecture of lecture 6.6 where we introduce Cohen's class of distributions. What we are going to do in this lecture is to revisit Cohen's class using ambiguity functions. We talked about this, but now it is time to look at the mathematical definition, and essentially we will ask how this smoothing the Wigner-Willey distribution, what it means in the ambiguity domain. In fact, now we are going to work in the nu comma s, that is the Doppler and delay domain instead of the time frequency plane. That is the central idea here, and we will show that smoothing the Wigner-Willey is nothing but, in fact, weighting. You should read the filtering as actually weighting the ambiguity function appropriately. Just to recap, the Cohen's class is either a convolution in the time frequency plane, as I have given in equation 1 here, or evaluating this generalized Wigner-Willey distribution with the help of this weighting or the parameterization kernel f, and this f is a function of nu comma s, and we said earlier nu is the Doppler and s is the shift or the delay, and what we are going to do in the next few slides is talk about this nu s plane where we will introduce the ambiguity function. And as usual, as we had before, the relation between the smoothing kernel in time frequency and the weighting kernel is through this 2-dimensional Fourier transform, where it is inverse with respect to one dimension and forward with respect to another dimension. Now, this ambiguity function is a function that measures the time frequency correlation. It was introduced long ago in radar signal processing by Woodward and is used extensively in both radar and sonar signal processing. It works pretty much like the Wigner-Willey. It gives a lot of information about the time frequency correlation, that is how the correlation, how the two signals are correlated in the time frequency plane. Now, the way it was introduced was completely different from the way Wigner-Willey was introduced. The context is radar signal processing, where one is interested in knowing the delay, in determining the delay between the transmitted signal and the received reflected signal. So, there is a radar which is trying to detect the location and the speed of the target. It does this by transmitting a certain signal at a certain frequency, and then there is a receiver sitting in the radar which receives the reflected signal. Once the signal hits the target, it is reflected back, and assuming under ideal conditions, that is there is no loss of the velocity and so on due to the medium which is typically air in radar signal processing, then what should happen is that the reflected one should be essentially a time shifted version of the transmitted signal, right. And in addition to that, there will be a Doppler effect, and I presume that you know what is Doppler effect. It is the perceived frequency of a moving object, right. When an object moves at a certain frequency, it is the at a certain velocity, then you perceive the frequency in a different manner. So, this frequency depends on the velocity itself, right. It is a classic example is the train coming onto a platform and then leaving. So, that is a classic example of a phenomenon where Doppler effect is experienced. So, in radar signal processing, the objective is to determine the location and the velocity, and this location is determined by first calculating the delay. Both are actually calculated, determined by calculating what is known as a delay, that is a round trip delay, and the so called Doppler, which is called the nu. This Doppler is a relative velocity relative to the speed of that frequency of the signal in the medium in which it is traveling, right. So, the ambiguity function is essentially a correlation between the signal and of course a reflected version of itself. You can define ambiguity function between two different signals because we are talking of radar signal processing. What we are doing is we are shifting. You can think of this x of t plus tau by 2 times x star of t minus tau by 2 in the same way as we wrote in the previous lecture, can be written as x of t prime times x of t prime, here I have s here. So, x of t prime times x star of t prime minus s. So, x star of t prime minus s is a shifted time shifted version, and the star is essentially to take care of the analytic representation of the signals. So, you are looking at this in the time frequency plane. How does this correlation change in the frequency in the time frequency plane? And therefore, to evaluate that, you take a you take a single integral with respect to the so called Doppler, right, and that is what you have here. And the ambiguity function is a function of this Doppler nu and the shift s. The reason for the name ambiguity is ideally when the shifts match exactly, then you want the ambiguity function to be 1, and when the shifts do not match, that is between the reflected and the transmitted signal, then you want it to be 0. Unfortunately, that is not going to be the case. The match between the shifted and shifted reflected and the transmitted signal is going to be non-zero, even though it does not exactly match the delay, and therefore, there is some ambiguity, and loosely people have called it as ambiguity function, but otherwise there is no ambiguity about the function value itself. So, you should be clear about that. So, coming now to the math, the ambiguity function is this integral here. It is a single integral of the, it is a Fourier transform of some kind of an instantaneous correlation. Unlike the Wigner-Willi, where the integrating variable is s, here the integrating variable is t prime. So, that is the prime difference. You can rewrite this ambiguity function in terms of the Fourier transforms of x and x star in the fashion that I have given here, where the frequency variable now, the dummy frequency variable is omega prime. Here the dummy time variable is the t prime. As I mentioned earlier, s and nu are known as the delay and Doppler, and you can read up any textbook on radar signal processing, which will give you more insights and into the historical development of this ambiguity function. The prime purpose of introducing this ambiguity function is to reinterpret Cohen's class, as I mentioned early on in this lecture, and it gives us a fresh perspective. To compare the definition of ambiguity function with the Wigner-Willi distribution, I have given you the definition of Wigner-Willi. As I mentioned earlier, when I evaluate the Wigner-Willi, the integrating variable here is t, whereas when I evaluate the ambiguity function, the integrating variable is the t prime. That means, if I were to write the Wigner-Willi for exactly with the same notation here, I would integrate with respect to s. Therefore, you should expect some parallels between Wigner-Willi and the ambiguity function. In fact, that is what is the case. The ambiguity function of a signal is a two-dimensional, again, Fourier transform of the Wigner-Willi. This two-dimensional Fourier transform again is the same case that we mentioned earlier, inverse with respect to one and forward with respect to another variable. So, this is the relation, formal relation between the ambiguity function and the Wigner-Willi. Now, you can start relating this to what we mentioned in the previous lecture. The Cohen's class is a smooth Wigner-Willi or a convolution of the Wigner-Willi with the smoothing kernel theta, and I can write the smoothing operation in the Fourier domain as a or the convolution operation in one domain as the product operation in the dual domain, and that is exactly what we are going to do now. We have already determined what is the Fourier transform of Wigner-Willi, which is ambiguity function, and we know already that the Fourier transform, two-dimensional Fourier transform of theta will give me f. So, you should expect now that the Cohen's class can be written as a product of the kernel f and the ambiguity function, and of course, an inverse Fourier transform of that will get me the Cohen's class. It is not exactly the Cohen's class, right. So, that is the basic point here, and also I should caution you, there are certain texts which will define ambiguity function in a slightly different manner, and you have to watch out for then all these expressions changing accordingly. And the one change that you will find in a few textbooks is, instead of the negative sign here, you would find a positive sign, and that changes the way you write this transform. So, everything else has to be consistent. So, when you are reading a textbook, watch out for these differences, but I have used the conventional definition of the ambiguity function. And also notice that we have switched the order with with the ordering of variables in Wigner-Willi and ambiguity function. In Wigner-Willi, the first variable tau has units of time t, units of time, and z has units of frequency, whereas ambiguity function has the variables ordered where nu is the velocity, Doppler velocity, and s is the s has units of time t. Before we proceed to reinterpret Cohen's class using ambiguity functions, it is interesting to note the certain properties of ambiguity functions, primarily because it helps us understand how interferences are removed in the ambiguity plane. We know already smoothing in the Wigner-Willi removes the interferences because you are essentially performing some kind of averaging in time and frequency. When we rewrite Cohen's class in terms of the ambiguity functions, we will notice something very interesting about the interferences, and that is related to one of the properties that I have listed here. The first property is that of the ambiguity function is that when I evaluate the ambiguity function along one dimension, I recover the respective correlation. For example, if I want to recover, let us say, the autocorrelation of the signal, then all I have to do is I have to evaluate the ambiguity function along the s axis itself. That means I set the Doppler to 0. These are called ambiguity functions with Doppler cuts and shift cuts or delay cuts. There is a MATLAB function also in one of the toolboxes, not in the regular toolboxes, which commercial toolboxes, which computes the ambiguity functions, and there you will see the term called Doppler cuts and delay cuts and so on. I think it is called the phase array toolbox or something like that. I can give you the exact answer in the forum. So, likewise, when I evaluate the ambiguity function along the Doppler axis, then I recover the spectral autocorrelation, right, of the signal, that is the autocorrelation in the frequency domain. In fact, there is something else that is not listed here I will talk about. Let me just finish. There is another property that is interesting. Once I finish discussing these properties, the energy of the signal, the interesting fact is the energy of the signal is the value of the ambiguity function at the origin. This is unlike what you see in Wigner-Willi, right? Wigner-Willi preserves the energy. You have to integrate along the entire tau z plane to recover the energy. Here I have to evaluate the ambiguity function at a point, and that point is the origin, and that exactly is on, which means now you should expect the energy of the signal to be concentrated around the origin. That is one of the key things that you start noticing, right. And obviously it reaches a maximum at the origin compared, the ambiguity function reaches a maximum at the origin compared to its magnitude at all other points in the nu s plane. There is a small mistake here, it should read as nu comma s, and we will correct that in both this expression in equation 5 as well as the one below. The ambiguity function, unlike the Wigner-Willi, is insensitive to time shifts, and therefore the magnitude is useful in radar signal processing, right. In Wigner-Willi we wanted time and frequency to be sensitive to time and frequency shifts, but the ambiguity function is not. In general, ambiguity function is a complex valued quantity. When we say it is insensitive, the magnitude is insensitive, as you can see from the expression here. Y is a time shifted and frequency modulated version of x, and the ambiguity function of y is again here it should be ambiguity function of x times the e to the j something. When I take the magnitudes on both sides, they should match, which means it is insensitive to time and frequency shifts in fact. And now coming to the most important one, well, one important point was the energy, that the energy of the signal is concentrated at the origin. Therefore, you should expect the signal components to be concentrated around the origin in the ambiguity function plane. The interferences, how do they map onto the ambiguity function plane or the nu comma s plane? It turns out that the interference geometry, unlike in Wigner-Willi, they are located far away from the origin. In the Wigner-Willi plane, that is the tau comma z time frequency plane, the interference terms occurred exactly midway in the time and frequency based on the time and frequency centers of the signal components. Now the interferences are going to be located far away from the origin. Let me explain that to you with the help of an example. So here I have for comparison the Wigner-Willi and ambiguity function on a signal that we have seen earlier. There are two atoms, one of high frequency and one of low frequency located at different time centers. This is the familiar Wigner-Willi we have seen earlier. They both are because of the amplitude modulation, these atoms are of finite width. What is of important to us is the presence of this interference term. The interference term is actually located midway in the time frequency plane with respect, not in the time frequency plane, but midway with respect to the time and frequency centers of the atoms. Whereas in the ambiguity function plane, that is the Doppler and delay plane, notice that I have delay or the S along the x axis and Doppler or nu along the y axis now for the ambiguity function. The center here in the contour that you see in the center of the delay Doppler plane is essentially the signal components, that is both the atoms, the signal components here, which are these two atoms, have mapped to the center at the around the origin. We should expect that because the signal's energy is the value of the ambiguity function at the origin. And what you see as circles away from this origin are the interference terms. So, what has happened is the ambiguity function has taken these two atoms in the time frequency plane and put them at the origin and taken the interference term and split them far away from the signal. So, it is exactly the reverse of what is happening of what you see in Wigner-Willi, and that is because of the dual nature of the ambiguity function and the Wigner-Willi, right. We have also seen this kind of duality between time and frequency in the classical Fourier domain. This is what is happening here. All the signal energy is concentrated at the origin, around the origin, and the interference systems are far apart. You may ask, what is the advantage now? Now, there is a big advantage because I know theoretically this is a property of the ambiguity function. If I want to remove interferences, what should I do? A common sense approach would be to apply some kind of weighting or windowing to the ambiguity function such that the window will only pick values of the ambiguity function within the vicinity of the origin and leave out the rest, and then perform an inverse Fourier transform. It will get me the Wigner-Willi, and that is it. So, I would have obtained the smooth Wigner-Willi. This is the basis for reinterpreting Cohen's class using ambiguity functions. In the smooth Wigner-Willi approach, we said these interferences that I see in the Wigner-Willi can be gotten rid by performing a time and frequency averaging in using a particular kernel. That now is equivalent to applying some kind of a weighting here in the ambiguity function or the delay Doppler plane, so that this kernel now in the ambiguity function plane will only pick values, give importance to values of the ambiguity function within the vicinity of the origin and leave out the rest, and then I perform the inverse Fourier transform, two-dimensional Fourier transform of that, I will get a smooth Wigner-Willi. That is the basic idea. So, with this idea we can reinterpret Cohen's class in two different ways, both lead to the same interpretation. The first one is the one that we mentioned earlier in the previous lecture, where I could write the convolution in the time and frequency as a product in the Fourier domain. We know that the two-dimensional Fourier transform of Wigner-Willi is ambiguity, and we also know that the two-dimensional of theta is the f, right. Now, all I need to do is to reinterpret. Let us look at the first one and we will talk about the second one. All I need to do that is to rewrite the Cohen's class as an inverse Fourier transform of the Fourier transform of the convolution. So, the first step is Fourier transform of the convolution. What does that fetch me? I know Fourier transform of convolution is a product. Product of what? Fourier transforms of the respective ones. The Fourier transform of W is ambiguity function. The Fourier transform of theta is f, right, which we denote as a theta here, but this a theta is nothing but f itself. And then I have to perform an inverse Fourier transform, and that fetches me the Cohen's class. So, that is a very straightforward reinterpretation of the Cohen's class, where now we call this f as the ambiguity kernel. This is just as a straightforward extension of the definition of ambiguity function itself. So, now f assumes this interpretation of being the ambiguity kernel. In fact, that is also what is the term that is used in Mallet's book and a few other texts. So, to summarize, in this approach the Cohen's class is nothing but the two-dimensional inverse Fourier transform of the weighted ambiguity function, and now I have a better feel for what role the f plays. Earlier we called this f as the weighting or the parameterization kernel. Now it justifies the terminology, it weights the ambiguity function within the vicinity of the origin. So obviously now if I want to choose f as a Gaussian one, it should have more weighting in the origin and less weighting. So the values of f should fade away as you move away from the origin in the delayed Doppler plane. Now you also understand why we use the same variables to characterize f. We had used nu comma s, and the same variables are used to characterize a. So all of that now becomes a lot clearer. The second interpretation is to introduce what is known as a generalized ambiguity function. It's the same thing. All we are saying is, first recall that the Cohen's class is a generalized Wigner-Willi, right. Now if I take the Fourier transform of the Wigner-Willi, I get the ambiguity function. So if I take the Fourier transform of a generalized Wigner-Willi, I should get generalized ambiguity. So what I do is I construct the generalized ambiguity and take the inverse two-dimensional inverse Fourier transform. That is exactly what I am doing here. I modify the ambiguity function with another function, two-dimensional function called C, and call that as a generalized ambiguity function. This C cannot be anything arbitrary. Again, I have to impose certain restrictions on C if I want certain properties on the Cohen's class. In fact, the C is nothing but f. You should have guessed that by now. The C, sorry for the confusion, the C and the same C I am using. So this is a small c. The small c is nothing but the f. Now the Cohen's class is nothing but the inverse two-dimensional Fourier transform of this generalized ambiguity function. So Wigner-Willi will give me ambiguity function, that is they are duals of each other in a two-dimensional Fourier sense. Generalized Wigner-Willi and generalized ambiguity functions are also duals of each other in the sense of two-dimensional Fourier transform. So the small c that we have introduced to modify the ambiguity function is nothing but the kernel f itself. So again this is another interpretation, but it is more or less the same interpretation that we have acquired earlier, which is that f plays a role of a weighting on the ambiguity function. Now just to give you a feel of how things look like, I have borrowed this figure from the time frequency toolbox tutorial, which gives you a fantastic overview of all the time frequency tools that you have. These figures are generated for three different distributions that we are familiar with: the Wigner-Willi, the smooth pseudo Wigner, the spectrogram, and the smooth pseudo Wigner-Willi. On the left, sorry, on the left, what you have are the weighting functions, that is the values of f in the delayed Doppler plane, and on the right you have the smooth Wigner-Willi. So what you can get from this is, let's start with Wigner-Willi. We know that to generate the Wigner-Willi, f has to be 1 along the Doppler plane in the delayed Doppler plane. We have seen that earlier, and what is shown here is not f alone. What is also shown is the Wigner-Willi of some signal, right. The middle term here are the interferences. Sorry, the middle what is shown here, although it says Wigner-Willi is weighting function, what is shown here is the ambiguity function. The middle one is the signals components, and the far off ones are the interferences. We have seen that, right, because we are working in the delayed Doppler plane, we are looking at the ambiguity function. Wigner-Willi does not perform any weighting on the ambiguity function, therefore there is no modification done. Simply an inverse transform of this ambiguity function will recover the Wigner-Willi on the right, and you see this presence of huge interferences, and these two dark lines are the signals components themselves. Do not worry about what is the signal right now. You can imagine what the signal has essentially two kinds of chirps, but there are interferences there, they are located differently. Now the spectrogram performs some kind of weighting on the ambiguity function. Recall we said earlier in the previous lecture that the weighting or the values of f that will generate the spectrogram is the ambiguity function of the window that I use in the spectrogram itself. Remember, spectrogram is generated from short time Fourier transform, there is a window function. We said in terms of smooth Wigner-Willi, the kernel is the Wigner-Willi of the window. In terms of in the ambiguity function plane, we say that the weighting kernel, which is the f, is nothing but the ambiguity function of the window itself. So that's exactly what's happening. If I, for a particular choice of window, the f looks like this. So what it is doing is it is picking values of the signal's energy and leaving out the interferences, as a result of which the interferences have vanished in the Wigner-Willi. But what has happened is, with respect to the original Wigner-Willi, I have some kind of smearing of the energy. This is the sacrifice that I am making, and the weighting here tells you why that smearing occurs. Lastly, we have the smooth pseudo Wigner-Willi, which performs a different kind of weighting. What is the prime difference between the spectrogram weighting and the smooth pseudo Wigner-Willi? Well, please do not tell me that it is the size of the window, right? Of course, that is just qualitative, but more importantly, it can take some interferences also with it when it is weighing the ambiguity function, whereas the spectrogram is the weighting function spectrogram only concentrates on the signal components. That is what we mentioned earlier when we discussed about Cohen's class. The smooth pseudo Wigner-Willi can produce interferences eventually, depending on how you choose your widths, right? If you choose a certain width of the windows in time and frequency that you have, it is a smooth pseudo Wigner-Willi, therefore it is a separable one. I have two windows to play around with, and depending on how I choose the widths, you can end up taking the interferences or not. For a particular choice, you will get spectrogram, but there exist a lot of other choices, and I am only showing you here the window that almost goes up to the interference, which is what is done in the time frequency tutorial, and therefore some interferences, very minor interferences can come in, but mostly there is none. In fact, if you slightly readjust this, fine tune this, then you will be able to get better energy distributions, better localized energy distributions than the spectrogram, and still be devoid of interferences. Right. So, there is again a reiteration of what we had seen with respect to another example previously. This way you can imagine the weighting functions for all the other distributions. In fact, just go through this exercise, take the kernels that we have listed in the table in the previous lecture for some well known distributions, take a signal, plot the signal's ambiguity function, and on the same plot plot the weighting function also, and see how the weighting function performs with respect to removal of interferences. If the weighting function is able to remove the interferences, you are guaranteed that you will get a positive valued distribution by virtue of Wigner's theorem once again. So, to summarize, what we have done in this lecture is reinterpreted Cohen's class using what are known as ambiguity functions that were introduced in signal processing, whereas Wigner-Willi distribution originated from a combination of approaches in physics and signal processing. But this shows that there exist a lot of parallels between the tools that originate from different domains, which is what we have also mentioned in the introductory lecture with respect to wavelets as well, where wavelets were introduced in different domains in different ways, but the ideas are more or less the same. The nice thing that we have seen here is the duality between the ambiguity function and the Wigner-Willi, and it gave us a fresh interpretation of the weighting function. So, hopefully you enjoyed the lecture. We will see again in the next lecture, which will close the topic on Wigner-Willi, where we will briefly look at the so called affine class of transforms. Here in the Cohen's class insists that the smooth Wigner-Willi satisfy the time and frequency invariance property. In the affine class, we will insist that it satisfies the time and dilation or the scaling invariance property. Then we will briefly talk about what is known as reassignment, which is more of a modern development, and close the topic on Wigner-Willi distributions. Thank you. No, Hemant. The example that we take up here for illustrating the difference between Wigner-Willi and ambiguity function, in fact rather than the difference, the duality, is one that is given in the tutorial, time frequency toolbox tutorial. It consists of 64 observations of a signal which has modulated chirps spaced apart in time, and you can read off the range of frequencies here that I have given. In fact, they are the same chirp is being modulated, sorry, the one chirp is being modulated with a Gaussian amplitude modulation, and there is another chirp which is being modulated with another amplitude, Gaussian modulated amplitude. Okay. So, now what we do is to generate a signal, we concatenate these two signals, and the signal here is shown on the top as usual with the spectrum here on the left panel of the figure. Let us come to the point. The point that we made earlier is that the signals components in the Wigner-Willi plane are located exactly at the point, respective points in the time frequency plane, that is at the respective time frequency centers, and that is what we see here in the figure. And the interference terms, as we know earlier, are concentrated midway between the time frequency centers of the respective components of the signal. When we move to the ambiguity function plane, which is essentially the delayed Doppler plane, the reverse happens. All the signals components are concentrated at the center, at the origin in fact of the delayed Doppler. This is an absolute origin here, and of course, what has happened is both the atoms, that is both the signal components, have muddled up here, they are all nicely and cosily settled. We know that the value of the ambiguity function at the origin gives me the energy of the signal. Now, the other important point that we learnt is that the interference terms move away from the origin, and that is exactly what has happened. The interference term that occurs midway in the tau z plane or the time frequency plane is now split apart, and it is located far away from the signals components in the delayed Doppler plane, and they are symmetrical. They are not really located at some arbitrary positions. There is also a certain geometry to this interference terms in the delayed Doppler plane. Now, the basic idea of constructing the smooth Wigner-Willi distribution is as follows, based on which we can now set the tone for reinterpreting the Cohen's class. The basic idea is to apply a weighting function in the ambiguity function plane, that is to pick only certain values and to leave out certain other values. That is the role of the weighting function. And what are the values that we are interested in? Obviously the signal. So, I apply the weighting function in such a way that it picks the values of the signal components which are centered around the origin and leaves out the values of the ambiguity function which are far away from the origin. Of course, what is far and what is near is what is determined by the shape of the weighting function itself. But once I do that, then what I have done is I have captured the signal components in the delayed Doppler plane. All I need to do to construct the smooth Wigner-Willi is to perform a two-dimensional inverse Fourier transform, and then I will get the smooth Wigner-Willi. Earlier we did this by directly working with the Wigner-Willi distribution itself, by subjecting it to a smoothing operation using a convolution kernel. The convolution now becomes a product. All I have to do is now multiply the ambiguity function with another weighting function, and this weighting function is none other than the f of nu comma s that we have seen earlier when we introduced Cohen's class, right. And we said at that time that we will acquire a fresh interpretation of the weighting function, and that is what we are going to do. So, with these basic ideas established, we can now reinterpret the Cohen's class.